Okay, so the last thing I want to talk about is sort of a question that you might have had before now, but what if f, the little one, doesn't exist? Because early on, we said that little f exists if, right down here, little f exists if capital F is conservative, but there's a whole lot of non-conservative vector fields. And in those cases, you would not be able to calculate this potential function f. So we're just going to go through the process for checking if your potential function actually works to verify that you started with a conservative vector field. So you're going to run into this concern or problem if a vector field is not conservative. In that case, there is no possible potential function f so that you get that nice property that capital F is the gradient of that potential function. So if you went through finding a potential function and you want to check if this happened to you, you're going to start from your answer f star. And when I say f star, I mean like this, oh no. This thing we went ahead and put in a box when we were done solving our problems. And you're just going to do a real quick calculation on it to make sure that everything worked out the way it should. You're going to rearrange your equations basically so that you solve for K1, K2, and K3. So if you go back to when we introduced these things, we should have that if you solve for K1, you get it from f minus the integral of your first component with respect to x. And if you want to solve for K2, you would get it from f minus your second component with respect to y, so on and so forth. And so we're just going to calculate those things and see if that's true. K1 should be equal to your answer minus a, the first component of capital F, integrated with respect to x. And you just need to verify that this should only have y and z in the answer because K1 is supposed to be a function of y and z. Then to check K2, you would take f star your answer and you would take away the second component integrated with respect to y. And when you do that, you should have a function that only depends on x and z because anything from y should have appeared in your integral and been caused by integrating b with respect to y. And then K3, you'll start with that f star and you'll subtract the third component integrated with respect to z. And in that case, you should only have variables of x and y left over. And so you're just going to check if K1 depends on x, or if K2 depends on y, or K3 depends on z, then something went wrong. Your f star, don't know what that is, does not work. Oh, it's probably the end of my K. And capital F is not conservative. And so I'm going to do an example where we knew it worked. We solved the problem, but this is just how we would check that it worked. And you're going to have some problems in your homework where you're asked to say if a vector field is not conservative. So this is the steps you would apply to that type of problem. So K1 should be f star minus the integral of a with respect to x. Oops. So what I did was I went ahead and I wrote down our answer from the previous example we did. That's going to be our f star. So we got 1/2 x squared plus 1/2 y squared plus xy. And then we're going to take away the integral of the first component, x plus y, with respect to x. But we calculated that already as part of the problem. The integral of x plus y with respect to x was 1/2 x squared plus yx. And so if we do this subtraction, we get 1/2 x squared minus 1/2 x squared and xy minus yx. And so we're going to be left with 1/2 y squared. And that depends on y. It doesn't depend on x, so we're okay there. And then for K2, we're going to again start with f star. 1/2 x squared plus 1/2 y squared plus xy. And then we're going to take away the integral of the second component, y plus x, with respect to y. But remember, when we were working through this problem, we solved for that. We could go ahead and plug it in directly from the previous page right here. We got that 1/2 y squared plus xy. So let's go ahead and just put that right in. Oh, sorry, 1/2 y squared plus xy. I think I must have just read that off wrong. Yeah. And then when we do that subtraction, the 1/2 y squared subtracts with the 1/2 y squared, and the xy subtracts with the xy, and we're just left over with 1/2 x squared. That's a function of x. It doesn't depend on y, so we're okay. So K1 doesn't depend on x, and K2 doesn't depend on y. So our potential function f works, and f is conservative. So f is okay. If you did this and you got like 1/2 y squared plus x for your K1, then that would be wrong. And f is not conservative, the answer doesn't work, and you're done with this. There is no little f that solves the problem. So that's how you're going to do that type of problem in this section.